Greetings, fellow mathematicians. In this problem, we're going to start to encounter partial fraction decompositions that involve irreducible quadratic factors. Now, the algebra does get more intense at this point, and we're going to take a look at an alternate method to plugging in called equating coefficients to solve for the unknowns A, B, C, D, however many we have. We'll mention that when that comes up here, but let's get started. Since our denominator is fully factored, we can jump straight to the partial fraction decomposition. So we have the linear factor x minus 1, and then the irreducible quadratic factor x squared plus 9. All right, for the linear factor, we get a partial fraction of the form a constant over the factor x minus 1. So we'll go with a over x minus 1. And then the big change for your quadratic factors, you get in the numerator two constants, something of the form a constant times x plus another constant. So our last partial fraction will get two unknowns, bx plus c, and then over that quadratic factor x squared plus 9. All right, so we have three unknowns here, a, b, and c. That's not too bad to solve for. We're going to still try to eliminate fractions. So I'm going to multiply both sides by the LCD, by this fully factored denominator, and the fractions, the denominator should cancel out everywhere. So if we do that, the left side will be left with that numerator, 5x squared minus 4x plus 19. And when you multiply the LCD to the first partial fraction, the x minus 1 factor cancels, leaving you with a times x squared plus 9. And then multiply your other partial fraction, the x squared plus 9 factor cancels, leaving you with the x minus 1 factor. Be careful to use parentheses. So I'm including that numerator with parentheses around them, and that's times x minus 1. All right, and this is where we're going to mention an alternate method. There's nothing wrong with the plugging in approach here. You could plug in, for this factor, the value x equals 1. Linear equations always have a solution. The problem is with your quadratic factor, x squared plus a number never equals 0. Now, if you're going to plug in imaginary or complex numbers, that might be of some use, but that's generally avoided in calculus 2. So instead of the plugging in approach, we would need three values for x. I guess x equals 1 would be a good value, maybe 0, and then another value. But depending on how complicated your left side is, and especially if you have any repeated factors, plugging in could be very, very tedious with respect to basic arithmetic. So let's mention an alternate method called equating coefficients to solve for a, b, and c. All right, we're going to take a look at an alternate method to plugging in values for x called equating coefficients. It gives you the same values, but sometimes it's beneficial, especially when you start to get into quadratic factors, either distinct or especially repeated quadratic factors. Now, I did write some steps like I would in class over here on the corner, and they're very simple, and basically it amounts to multiplying out, expanding the right-hand side. You're going to get a bunch of powers of x, and since this is an identity, it should be true for all values of x. Basically, the coefficients of powers of x on each side should be equal. Now, again, this is still tedious, but sometimes the algebra multiplying out is easier than doing powers of numbers. Like think of 2 to the 5th power minus 16 plus 1. I can barely do that in class. I'm much better with algebra. So let's go through equating coefficients. First step, we're going to fully expand that right-hand side. I'm going to write the left side down for consistency. All right, and let's just take our time. We're going to multiply a through. We'll get ax squared. Multiply a again in. We'll get 9a. And just be careful here. We're going to FOIL this. So we'll get bx squared. Looks like we get a minus bx plus cx and then minus c. All right, so that is step one. We have a bunch of terms here. Some of them are like terms. Let's go ahead and combine them. And I'm going to notice we have x squareds and then going down in powers. So let's collect first all of the x squareds. Looks like we have an a and a b x squared. We're going to factor out x squared from them and basically have their coefficients in front of x squared. So we're going to write that as a plus b x squared. Nice little technique I like to do in class, especially when the kind of right-hand side is a lot more complicated. I like to just cross the terms off that I've already used. They're not canceling, but I'm just crossing them out, so that way I don't have to look at them anymore. So let me cross off the a and b since we already used those. Let's go down to now looking for coefficients for powers of x. And we have our first one, negative b, and then positive c. We can factor x out and write that as c minus b times x. Cross those out. And what we should be left with for this quadratic polynomial, we should have x squareds, x's, and then constants. We have 9a minus c. All right, and that is the second step of collecting like terms just from the right side of what we multiplied out. The left side, we're going to keep that the same. And this is where we can now go to step 3, which is usually the part that's a little bit complicated for students, but it's actually really simple. We're going to notice the coefficient of x squared on the left is 5, but your coefficient of x squared on the right side is a plus b. And that gives us one equation. We're going to need 3 equations to solve for the 3 unknowns. The 3 equations we get will be equating coefficients of x squared, x, and then the numbers, the constants. So let's go ahead and write them down. All right, and our 3 equations, first equating coefficients of x squared, coefficient of x squared on the left is 5. And your coefficient of x squared on the right is a plus b. All right, that's one equation. We need 2 more. We're going to now equate coefficients of x. The x coefficient on the left is negative 4. And on the right side, your coefficient of x is c minus b. And your last equation, coming from equating the numbers, the quantities without any x's on them, left side, that constant is 19. And on the right side, your constants are 9a minus c. All right, and this is where most of students start to struggle. This is very simple. This is 3 equations and 3 unknowns. There will be some examples which might involve 5 unknowns, so you'll need 5 equations, and it could even get up to maybe 6 equations and 6 unknowns. That's probably the highest I would go with my Calc 2 course, either in class or on an exam. All right, so let's go ahead and take our time with this. There's generally no rules to this, so anything goes. Think of systems of equations, substitution, or elimination. You could also use linear algebra methods if you know that, but we'll stick with substitution and elimination here. And there's actually some nice symmetry here going on in the equations. Now what I'm going to notice is just by taking a look at the first two equations, I have positive b and negative b. If I add those equations, I can get the b's to cancel. So let's add the first and second equation. All right, we're going to add the left sides. That should become 1. We have a, we have c, but the b's cancel. So we get another equation, 1 equals a plus c. And if you look at your third equation, that involves only a and c. So by adding these equations, we've reduced a 3-system equation involving 3 unknowns to now a system of 2 equations and 2 unknowns. All right, so let's write this equation with that. We're not doing anything to the third equation. 19 equals 9a minus c. And again, we can notice here positive c, negative c. Let's go ahead and add those equations. And we should find that the c's cancel, and we get a very simple equation to solve for a, 20. And then add your coefficients here of a, 1 plus 9, you'll get 10a. All right, and that is very simple to solve. Solve that for a, you should get a as 2. All right, we need the values of b and c still, but if we take a look at some of our equations, that's actually going to be really easy. With a as 2, let's take a look at this first equation. Plug in a as 2. 2 plus b equals 5. B must be 3. And to get the value of c, we can look at this equation. If a is 2, 2 plus c equals 1. That should give you that c is negative 1. So what might have been intimidating, just with a little bit of thought, actually isn't too bad, at least for this example. Now, equating coefficients was the method that we used for this. Probably don't need that for linear factors, but equating coefficients is a great technique when there's quadratic factors involved. If you were to plug in values for x, you would still get the same values for a, b, and c, sometimes with more work, sometimes with less work. This is just another technique to have in your mathematical toolbox. Now with your values of a, b, and c solved for, that is most of the work, and we can get straight to integrating. We're almost done. Our last step is just to integrate. We're going to plug our values of a, b, and c back into the partial fraction decomposition, and we'll arrive at this integral that we need to evaluate. Now the first term, that's going to be straightforward. The first term integrates to 2 times natural log of x minus 1, so that shouldn't be a problem. But what is a little bit tricky is this second term that we need to integrate. The best tip I can give you when dealing with bx plus c over a quadratic factor is to split that apart. In other words, we're going to split it apart into 2 fractions, just using some basics of fractions. So let's go ahead and write that down. We're going to split this as 3x over that denominator, and then minus 1 over that denominator. All right, don't forget your first term. That we're not doing anything to. But we get now 3x over x squared plus 9, and then minus 1 over x squared plus 9. All right, and that makes the last integral much more manageable. All right, Now let's go to the second term here. That we can integrate with a straightforward u substitution. The last integral here, that comes down to an integration formula that gives us an inverse tangent. So let's go through the work for the second term. So we'll evaluate the integral of 3x over x squared plus 9. This is a straightforward u substitution. We'll go with u as x squared plus 9. Calculate your du. You'll get du equals 2x dx. And since we're missing a factor of 2, divide your 2 over to get 1/2 du equals x dx. We have all the pieces to convert from x's to u's. And if we do that, we should get as our simpler integral, we have a factor of 3 times 1/2. We can write that as 3 over 2. And then times 1 over u du. And now we can recognize that as having the antiderivative of a natural log of u. So this will integrate to 3/2 natural log of u. And as always, back substitute your u, which is x squared plus 9. All right, so that completes the evaluation for the second term. The last term, we're not going to do any work. We're just going to recall the formula that we need. And we'll write that formula down first. Hopefully you know it. That formula is going to be the key to making these questions go as quick as possible once you start dealing with quadratic factors. The algebra goes up. So you'll definitely want to make use of this formula, and it is the integration formula for the integral of 1 over x squared plus a number squared, a squared. All right, the formula here, what we get, this integrates to 1 over a times inverse tangent of x over a. And I don't expect my students to prove that during a partial fraction decomposition question. I just tell them make use of that formula. You can prove it earlier with a u substitution if you really want to, but I don't have any expectation for my students to do that. Hopefully your professor doesn't either. All right, so let's just make use of our integral. We'll put it right below. Our integral is 1 over x squared plus 9. And to use that formula, we just need to identify the value of a in the formula. Now, the formula has a squared. We want to look at our number in the denominator as a perfect square. And fortunately, 9 is 3 squared. So our value of a that we're going to be using is 3. And we just need to now plug it in, and we get as our antiderivative 1/3 times inverse tangent of x over 3. That's pretty much all the work for this problem, the algebra and solving for a, b, and c, and then the evaluation of those second and third terms in our integral. We just need to plug everything back in. But don't forget to integrate this first term. That's the easy one. We get as our antiderivative 2 times natural log of x minus 1. The middle term, we integrated that as 3/2 natural log of x squared plus 9. And then our last term, we integrate that to 1/3 times inverse tangent of x over 3. Don't forget your minus. We get this as minus 1/3 times inverse tangent of x over 3. and as always, your plus c. And there we go. That is a complete medium difficulty partial fraction decomposition question, which involves quadratic factors. If you enjoyed the content, support the channel, make sure to like and subscribe.